Hi, my name is Pallala Murali. Now I am explaining about sputter deposition. PVD process, bombardment and removal of the cathode material with positive ions from the rare gas discharge, originally developed to deposit refractory metals. Now the sputter deposit is able to deposit most materials. Now I explain about sputter deposition system. In sputter deposition system, there are six types: vacuum chamber, sputter sources, substrate holder, pumping system, vacuum gauges, gas flow supply. Sputter deposition process. First, we have to say about sputtering. We want to know about sputtering. Ions are accelerated into target. Some of the surface atoms are sputtered off of the target. These sputter atoms flow across the chamber to where they are deposited. Now I am saying about mechanism of sputtering. Sputtering involves the collisions of energetic ions with a target surface, and the process usually leads to ejection of target atoms. Sputtering alloy targets. Composition of alloy in the film is approximately the same as alloy in target. Slow diffusion mixing in solids. Target reaches steady state. Surface composition balances sputter yield. I will explain advantages of sputter deposition. Elements, alloys, and compounds can be sputtered and deposited. The sputtering target provides a stable, long-lived vaporization source. In some configurations, reactive deposition can be easily accomplished using reactive gaseous species that are activated in plasma. The source and substrate can be spaced close together. The sputter deposition chamber can have a small volume. There are disadvantages of sputter deposition. Sputtering rates are low compared to those that can be attained in thermal evaporation. Sputtering targets are often expensive and material use may be poor. Most of the energy incident on the target becomes heat, which must be removed. In reactive sputter deposition, the gas composition must be carefully controlled to prevent poisoning the sputtering target. Basic techniques in sputtering: DC sputtering, RF sputtering, magnetron sputtering, reactive sputtering. Now first one, DC sputtering. Light E pulled towards walls faster than ions, leaving slightly more than ions in glow region. Light negative move away from cathode faster than ions, leading to a large field. High acceleration of ions into cathode. High E ions knock target materially loose, resulting plume of neutrals. New electrons from impact reactions replenish the plasma. Another one, RF sputtering. DC sputtering. What about dielectricals? In DC systems, positive charge builds upon the cathode. Need 10 power minus 2 volts to sputter insulators. RF sputtering. Frequencies less than about 50 kilohertz. Electrons and ions in plasma are mobile. Both follow the switching of the anode and cathode. Basically, DC sputtering of both surfaces. Frequencies about 50 Hz. Ions can be longer flow the switching. Enough electrons to ionize gases. Magnetron sputter deposition. Use with DC or RF. High sputtering efficiency. Why? High sputtering rates at lower air pressures. Fewer gas collisions, more line on site. How? Increase probability of electrons triggering air. Increase electron path length. Use electric and magnetic fields. Magnetic sputtering principle. This technology uses powerful magnets to confine the glow discharge plasma to the region closest to the target plate. That vastly improves the deposition rate by maintaining a higher density of ions, which makes the electro or gas molecule collision process which more effective. Reactive sputtering. Chemical reaction takes place on the substrate on target. Can poison target if chemical reactions are faster than sputter rate. Adjust reactive gas flow to get good stoichiometric without incorporating excess gas into film. Reactive magnetron sputtering zinc oxide thin films. Zinc oxide is one of the most interesting second or four compound semiconductors. It has been investigated extensively because of its interesting electrical, optical, and physioelectric properties. Thank you.